Okay, hi. I'm Peter and I will be talking about source code and ThreadScope. First, small apology. I'm talking about viewing, which is a process. So this is sort of a report of where I am. I'm not finished with this. And there's still quite a bit of stuff that needs to be done for this to become truly finished, truly useful. So, but this is where. Okay, we've seen all this before. ThreadScope basically works this way that you have your share program, put it in GHC, compile it with some options. Then you have your execute table, execute that with some options, and you get an event log, then you have ThreadScope, which visualizes that whole thing. So then we get a view which might look like this. So we saw a few examples in Duncan's talk where we obviously see that there's a problem with parallel execution. In this case, we have 4 cores, and well, we seem to be executing quite well. I mean, we are only getting a speed up of 2.5 maybe out of it, but there isn't a problem with parallel execution here, I would say. So, by looking at this, you would say, okay, ThreadScope seems to be pretty useful in this case. We would have to look maybe into this. What is actually, how much productive work does that actually mean? So, let's split out a bit more. Here we now have a list of what Haskell was actually doing in that time, at that point in time roughly. So you might see, might be pleasantly surprised, that in this program, our worker function, save, is actually at the top of our list what was happening at that point. On the other hand, it's not that good, 23%. So we have lots of overhead at this point. Well, where's that coming from? We might dig a bit deeper. This is core. This is what GHC translates the program into before it goes into the direction of imperative code. So maybe that was well visible. We have a function from int to int, int list to bool, and in core this becomes pretty much the same thing. Int list to something. Problem being, this is all boxed. We have a lot of lazy operation going on here, which isn't really what we had in mind, because this is actually meant to be tied in a loop which goes over the list. So what we might do then is maybe add some strictest annotation, just post some banks here, and all of a sudden we see, okay, our work is actually now at the top of the list, and the overheads that was dismissed has come back to a very low value. So we might actually be a lot more satisfied with this program. So this is a very basic example, but it should have shown that this is useful. This is our goal. We want just to click somewhere and then have information on what source code executed there. Let's break that down a bit. We need first accurate profile. When we have a profile program, we want good information what executed at some point. That's also a bit more second point. Obviously, we can only measure the profile program. What we're actually interested in, though, is the original program without profiling, because that is what we were using in the end. So we need to make sure that we're not having too much overhead there, that we are not going into the way of optimizations too much. So we can actually learn something from the profile. We also want good time resolution, that we actually know, okay, this is executed at this point. So we need to generate enough data to make that possible. Source code annotations, we want to, from the data, from the profiling data, to find a good way back in the source code that we're actually pretty sure that this is the source code that was responsible for the cost. And also we would like maybe a number of extra features like being multi-core safe, like saying, okay, this baby executed on this multi-core. Might actually be interested in low-level features like cache misses, all kinds of things. So how would we do that? Well, first, the basic problem here is that we're talking about lots and lots of information here. So if where every time we went to a procedure, generated an event, okay, we went to this procedure at that time, now we went to this procedure at this time, there would be so much data we couldn't possibly retain. So we need to throw a lot of it away. So how do we do that? We do that by saying we close to what the true distribution would be like. And the thing about that is we can also do other periods here. So if we say, do it like this, we might get a different distribution. Say we do these periods, we use, say, how many cache misses happened at that point. Then we get a hotspot profile for caches. So how do we implement this? The perfect way of doing this is getting hardware support for it. Luckily, today's processors have so-called buffer performance counters, which are registers in the processor which count, say, cycles or cache misses, all kinds of low-level events. And we can program those to interrupt our program at certain points where we then can do the sampling. That's a very good thing to have because we kind of have a outside view. We don't need to change the program for this at all. It is pretty fast because we have an hardware implementation, and it's flexible that we can use, we can collect a number of different statistics. On the other hand, operations system support is a bit more shaky. If somebody knows how to get to them on Windows or Mac OS reliably, I would be very interested in that. On Linux, it's pretty easy. We have PAPI and perfwins. Those are great interfaces. Otherwise, I'm not so sure. So, being that it's not really that good that we can only do it on Linux, we need alternatives. First idea would probably be we just use plain timers. Whether it works, I guess, but there are a few small problems with it. First, we're not really that interested in time. We'd only be interested in time if we really knew the program was executing all the time. That might get descheduled and that might introduce noise. Also, we need a lot of data to be able to say something about every point in time. And under 10 milliseconds, timer supports also seems to get a bit shaky. Other alternative is that we could instrument our code. So for every piece of code that GHC generates, we put kind of a prefix to it that notes down some data. Obviously now we are talking about changing the program, and we might get slow. That's just pretty much for reading the cycle count of the processor. We are already at 60% slowdown in for our program. So bottom line, I currently have concentrated on implementing the hardware performance counter support and this instrumentation for the server side. So now we have by now we know how we collect our data. But what data are we actually collecting? We want to know what source code was executing at that time. Now there's already an interface, an implementation for that, which is cost centers in GHC. That works by inserting those cost centers into the code, either automatically or manually, and then GHC makes sure that this association stays one-to-one pretty much till the end, till we are generating a sampler. That gives us both source attribution, but maybe, as I said earlier, that we might get into the way of optimization that way. We might get a subtly different program. And as I have shown in the example, often we might, our main purpose might actually be to find out which optimization GHC did and which it did not. So for our profiling changes that, it's not really good. Second reason being that if we're talking about those low-level counters like or something like that, we don't really we don't change the program, and we only get something like the instruction pointer back. So we need a way to work our way back to the source code from that. So the idea here is that instead of putting this as instrumentation as part of the code transformations, we try to just follow them through GHC and see what information we can get out of that. And we get maybe worse source attribution, but at least we're sure that we're still talking about the same program. So, we need to follow the source. What do we need to follow it through? This is a kind of high-level view into how GHC operates. We might start with the source code, then this gets put into a functional representation, which is core, then it gets optimized a bit, then we get an imperative representation, gets transformed to imperative representation, which is C minus minus, and that gets optimized a bit. Then we represent assembly, link all that together, and get the final program. It gets a bit more tricky if code gets integrated, say inlined, or rules get applied. Then we have to make sure that we have to think about that we might actually, our annotations might start covering more code than we actually want, or annotations might be removed in the case of rules. That's a bit more tricky to get it right. So, let's say we now have for with all our annotations still in place, optimized, and now we want to get to the C-minus stage. So what happens at this point is that each of those functions will get transformed into one or more procedures, each consisting of blocks, each consisting of instructions. So if I really wanted to get the fine-grained view, I would now have to look at every instruction and say back, okay, coming from a hello world, blah. But that's not really practical, at least not if you don't want to change a lot in GHC. It's actually not needed, because the way that procedures are generated, they are often covered by the same annotations anyway. Currently using covered style ticks, and they tend to clump up pretty much at exactly the positions where procedures are generated. So what I'm doing instead is that I'm breaking out the data. That's the NPO anyway. So here I'm saying, okay, A has these annotations, B has these other annotations. There's also a great place to know back what core these procedures are generated from, which can be useful in diagnosis data. So last step. Now we have all those procedures, and now we want to generate an executable from it. Problem being here, that's actually not something that is completely done by GHC. This is done by native code generation, assembler, GGC, UM, depending on how we do it. So when we want to retain our map, we need to speak a language that these tools understand. So what I'm actually doing is I'm generating dwarf information, which is the standard way that C programs will track the debugging information. Obviously, can't really capture everything that I have in terms of the scarce source code informations. So I'm putting the rest in the binary as sort of a block, which can get the input at the start of the event block later. So that gets a bit much. So where are those informations all coming from? We now have the source code, which obviously ThreadScope needs to read in order to present us this view. From the application right now, it reads a dwarf. And from the event block, it will now read the map with all the information of where the source code locations actually, how those map to the addresses in the application, as well as the event, as well as the sampled our samples from instruction. So now we have all this data in ThreadScope. What do we do with it? There's still a lot of work here to do. This is just a few picked out issues that I have solved or at least partly solved for this view. One of them being, I said, that we want to click at some point and then want to get a rough approximation what execute. Now, obviously these samples are spread all around the timeline, so I can't really say I picked one. Instead, what I'm doing is I'm weighting them by distance to the click and make distribution out of that. Other problem being, as I said earlier, one function in core or in the program actually can generate a lot of procedures. So if you saw to start this example, we had everything was saved with a lot of entries here. So the reason being here that this was the sign of lazy iteration. GHC was splitting this in parts and taking it back to be executed later. So is this a good thing or is this a bad thing to show this? I mean, I guess it can say either way. On one hand, I might be very interested to see, is this my function actually becoming one backend function? Or is it actually being split this way? On the other hand, it might get hard to find out how much cost actually gets associated with one function. You might also have the other problem. As I said earlier, inlining might actually my notation might actually end up covering more code than I wanted. which just picks out the biggest chunk of code and directs it over there. It would be good if I had a better solution for that. So, by that we're pretty much finished. Where am I? I think I have a pretty good core profiler so far, which, well, you could say is useful, is maybe not useful. Two things are still pretty much missing. The code association can probably be improved quite a bit. Samal was also working on this. It might be an idea to kind of draw all those source code annotations, which have been done in a number of ways on cost centers, coverage, breakpoints, whatever. All that could be probably run into one and improved on top of that. On the visualization side, as I kind of hinted, I also see a lot of room for improvement. So we'll see what can be done there. So far for that. I would really appreciate a discussion.
People might be wondering when they look at this, why I'm making everything so complicated, why I'm holding
responds to so much data. The idea is that then I can find new and interesting ways to visualize that, and maybe remove then a bit of the complexity in the user interface. Okay?
So I think Performance does a heat map, basically. You ask Performance to find something, it will give you assembly instructions, right? And left column is like a percentage, basically, of how much time how many samples were found at each point. Then if you track that back to source, you can have a heat map going to the left-hand side of the whole source program.
Shape's scheme actually spits out an HTML copy of the code that has the code.
Right.
That's what you would.
Yeah. Problem with that obviously being that it gets, at that point I really need very, very good source code associations. And I mean, I could probably, the easiest thing to do would probably be to do it with for. So there I kind of, not really one-to-one, but I could get a lot more fine-grained. I mean, yeah, I'm actually subsuming some things in this already, which I could then piece apart once I show the core. I'm not doing it currently, but that's. Okay.
So I'm just sort of on the same theme. It would also be helpful to sort of integrate this with HPC. So I can just say, okay, well this function is high, but HPC can actually say which branches are actually. So even if you can't get granularity from this, just sort of getting interoperation with HPC would be, I think, would be helpful.
Yeah, that's pretty much what I'm talking about. Yes. Right now I'm not tracking those branches. Right now I'm just staying on the function level and blaming the whole function. But yes, branches, that's something I want to look into.
I don't know how much runtime overhead you buy, of course, when you use HPC. And then again, you might want to have that trade-off. Yes.
Wasn't there a tool once which allowed to use HPC only for time fractions?
I don't have something like that. The problem with using, the problem that we discovered with using HPC is that HPC tells you when it has executed, but it's not accurate at telling you how many times. These transformations can mean that they get posted out of loops. So it might only count once, but actually the loop executed a million times. So actually HPC at the moment isn't useful for that.
Yeah, well, that will be fixed.
But yeah, you can decide on the
Yes.
It's awfully expensive though.
But yeah, HPC is an instrumentation grid, which is inexpensive, which is what I'm saying.
Well, HPC is actually not that expensive. I mean, relatively speaking.
I'm not changing the bits to counters, which probably make
They're all
it.
counters.
Oh, they're already.
I mean, you could probably, if you really wanted to get HPC to get more efficient. I mean, right now what happens after optimization is that a lot of those things actually clump together. So you could probably try optimization path, which reduces the number of counters used for the whole program. And then HPC could probably be very efficient.
But also we were looking at deep trace, which is this dynamic tracing. Yeah. Because they pay a lot of attention to being as non-invasive as possible. I think their overhead is 8% or so. So if they have more dynamic application approach, they let it turn on and turn off probes. It's not quite the same. But they do it basically by post facto modifying code against one.
Yes, the problem being with source presentation, that's kind of one of my first slides. If I then, we're talking about putting one dtrace style probe at the start of every procedure. If we then turn on dtrace, it will probably be too much cost to be really realistic. I really want to get into this direction. Once we're talking about more high